Welcome to Engineering Scale Models. I'm Jason, your host, and I do models. Today we are looking at programming my Mojo V3 clone part 2, and we're going on the tutorials from Alcatree, their synchronous logic tutorial. So let me go to the tutorial page here, right there, and then let me that down. You think 3 monitors would be enough, but it's definitely not enough. So let's go to this here, and let us first this. Okay, so now we are set up. We have the tutorial and we have our base program opened up. Now, let me see, does this have, well, we're just going to start a new program here. So, this is basically synchronous logic. We want to blink an LED, and it talks about the clock and how things trigger on the rising or falling edge of the clock, and it can only be a 1 or a 0. And in this episode we'll be using a D flip-flop. A D flip-flop has a D input, a Q output. It has an enable signal, so you can enable it to take in the value of D whenever there's a rising edge of the clock. Or you can, have clock pulses and not enable it and keep and store the value of D. And then there is also a reset that is asynchronous, which means it resets the flip-flop to the Q to a 0 or a low, even if the clock cycle is not pulsing. So it is a reset, and it talks about how we want to loop through blinking the program. And if you do that with just an inverter, it would go indefinitely, but it would run at the full 50 megahertz, and it would give you a bunch of errors and glitches, and it wouldn't work out that way. It would just stay on in like half volume of brightness. So we're going to implement a D flip-flop where D comes in and then Q comes out with a clock and reset. We're going to ignore the label, the enable, not label. So first we need to create a module. So we're going to open Arco Labs and go to new project, and then we are doing Lucid, and we are going to name it Blinker Demo, BLINKR, Blinker Demo. It is a Lucid project. Created. It already exists. We're going to overwrite it. Okay, so we've done that, and now under sources, now the file should be under sources. Okay, so now we got to click the new file icon, and then we are going to name this Blinker, and it is going to be a Lucid source. Okay, so this is what we have. We have this module here with an input clock, and then we have input reset, and it's showing us some errors here because we haven't defined anything, and then we have an always out. So if we come in here, it shows us that we have the exact same thing, and now we need to add the digital flip-flops. Now we're going to put the code in and then go over what the code says. So we're going to come in here and we're going to do a digital flip-flop CONUT counter, and we're going to put a bracket 25 because we want it 25 bits long, and then we're going to feed it the clock signal, which is TLK, And then where is it getting that signal? It's getting that signal from the clock. And then we're going to comma, and we have to feed it the reset signal. And it is getting the reset, RST, reset signal from RST. And then we need our closing parentheses, semicolon, and we still have some errors, but that's okay. And then on our always block, we are going to come down here, and then we are going to go to blink, blink equals count counter dot q, and then it's going to give us q at the 24th bit. So it's gonna, we're actually dividing the 50 megahertz clock down by doing this. So we don't need out anymore. So now we need count counter dot d equals counter dot q plus 1. So we're going to add 1 to the counter. So we got a lot of errors here. I don't know what's in it. The name counter could not be resolved. CO, that's why. COUN. Let's solve that. And blink. And this needs to be changed to blink. So our output is blink. So we've taken care of all of our errors. We've labeled things. So there's that. Now it wants to go over here. So in line 7, let's make this equal what they have. So line 7 has our D flip-flop. Oh, first he renamed the output blink. See, I missed that the first time. So declaration of the flip-flop. Lucid has a DFF for creating flip-flops. The flip-flop I created is called counter and is 25 bits wide. And then we connected the clock signal, and I showed you how to do that. In the always block, line 10 simply connects our output blink to the most significant bit of Q, of the counter's output Q. And when you're working with flip-flops, FSMs, or modules, use the dot syntax to specify what signal you want. In this case, we need to read the Q output of the digital flip-flop. So we use counter.q, and you can see that we did that, and we fed it the 24th bit in the brackets. The next line of the code connects input D, which is of the DFF digital D flip-flop, to its output Q plus 1. So we're changing the value of D to Q plus 1. This means that every time the clock goes high, the counter Q will be increased by 1. When declaring a digital flip-flop, a D flip-flop, or a fine state machine, you must connect the clock input and optionally connect the reset. These cannot be connected later in the always block. We did this, and then we connect the reset signal to the counter. What does this do? Whenever the reset signal goes high, the value of counter Q becomes 0. This is also the value of the counter is initialized when the FPGA first starts. If we wanted the counter to initialize and reset a different value, we could specify the value using the DFF parameter hashtag INIT, and then they fed it the value 100. Now it'll start at value 100 and reset to 100. The default value is, if none is specified, is 0. And parameters are hashtag name instead of dot name, and parameters are always capitalized. If you don't need to reset it, you just don't connect it. Now, here's what the counter circuit looks like. Keep in mind there are actually 25 flip-flops, but only one circuit, and the connections are actually 25 wires or 25 bits wide. When many flip-flops are used to store a single multi-bit value, they are commonly drawn as a single flip-flop. So this is what we have, the +1 thing, and then it stores it. Let's look at what this module will actually do. Right after the reset signal goes low, counter.Q will be 0. That means the counter D will be 1, since our combinational logic blocks assigns it counter Q +1. At the next positive edge of the clock, counter Q will be assigned the value of counter D, or 1. Once counter Q is 1, counter D must be 2. So you should be able to see what will continue to happen. Each clock cycle, counter Q will increase by 1. But what happens when counter Q is, 25 bits and it's all 1's the max value? Since we are adding a 1-bit number to the 25th bit, we can actually result up to being 26 bits. But since we are storing it into a 25-bit D flip-flop, we lose that last bit. That means when the counter Q is at its max value, counter D is 0, and the process starts all over again. So our counter will continuously count from 0, what is that, 1, to 33,554,431, or 2 to the 25th minus 1. And then how do we make an LED blink from this counter? It's simple. Once you realize that half of the time of the most significant bit is 1 and the other half of the time the most significant bit is 0. Because if counter Q is less than 16,700,077,216, or 2 to the 24th, then the 24th bit must be 0, and when it is equal or greater, the most significant bit must be 1. That means we can just connect the LED to the most significant bit of our counter. If you need to convince yourself that this is true, try writing out the binary value from 0 to 7 and then look at the most significant bit. Most significant bit changes. So how fast will it blink? With the Mojo, every 0.67 seconds, because it's a 50 Hertz clock. Now we have to connect this into the module. So in Lucid, there are specific ways to connect it. So this is where we can have different counters, a 12-bit counter, a 7-bit counter, an 8-bit counter. I'm going to take this into a future project, but right now we need to click on Mojo, and we need to go open up the top file. So we need to go to the top file, and we need to clock reset condition, always reset condition. So we need to go to LED here, and we need to go to 8x curly bracket my blinker dot my blinker dot blink in the curly bracket. Okay, and then under this reset condition, we need to put in .rst, and we need to pass it the RST location, and then we need to curly bracket it and to pass it that module and name it my blinker, and in the curly bracket. So that is that. So then it talks about the nested clock signals, and then now all LEDs should blink about 2 times a second. Well, ours is a little different because we have a Mojo. So let's let's build the project here. Checked it. We're good. Now we're going to build it. It just tells us some things were never used. So we're going to plug the Mojo in. You can see it light up there. And it is still... So why that does that, if you look back up here to these different counters, hopefully you guys can see this. If you look up here at these different counters, you can actually set up 3 different counters in this section. And then if you look back to where we use the counter blink, you can set up a blink 1 equals counter 1, a blink 2 equals counter 3, a blink 4 equals counter 4, and you could do 8 different counters, different bits wide. And then when you get to the module down here, you can set these to, instead of LED, all 8 LEDs equal this, you could do each individual LED with each individual blink number. So one could be blink 1, one could be blink 2, all that stuff. So you know, this calls the blinker program and it names it my blink. So then you could, you know, blink 1 and then LED 1, blink 2. You know, you can go through and do that. This signifies all 8 LEDs. But if you look, finish building the project. If you look at your constraints here and you come over here, it tells you the LED 0, 1 through 7. So you can see what your LEDs are labeled. This is your constraints. This is where all the pins are that the outputs show. And you can see 8 up here. So let's go. Let's download this project. Now, I already made this video once and the audio crapped out, so I had to make it again. So let's see if our lights are blinking. Can you see that? As you can see, our lights are blinking. So, and then we can reset it. Okay, reset should have did something. There it goes. It's blinking again. It took a minute. But as you can see, very simple. That is this synchronous logic. For the beginning of the next video, whatever the next, let's see what the next topic's going to be. Tutorial. Okay, there we go. Click the right thing. So that was synchronous logic, and then now we're going to look at the I/O element, which means we're going to use the I/O board, which is this shield on the top here. So we're going to be using this I/O shield to do different things. And I've already tested the demo, but I haven't tested this base code. So that's going to be the next topic. I'm going to do something with the counters and see if I can do some cool stuff to show in the beginning of the next video. But that is going to do it for this video. You can visit me on these social media links. You can also support me on Patreon. And there's also a GoFundMe page in there so that I can afford some test equipment for my bench. And if you want to see the test equipment I'm using, it is... There it is. There's the test equipment on my bench. It's singlet test equipment. I have the scope, the power supply, the arbitrary waveform generator, the electronic load, and 2 of the meters. They're on loan to me for about 2 months, and I can purchase them at a discount. So if you guys want to help support me, you can donate to help me afford this equipment so I can continue to do some cool projects and, you know, troubleshoot some cool stuff. But we're going to be doing some heavy logic in this Mojo in the future, and it's going to be handy to have this, plus the logic analyzer on the scope's going to come in real handy. But thank you so much and have a fantastic day.